Welcome to our Spiral 6 review. This calculator active spiral will cover topics that include product, quotient, and chain rules, some graph identification based on f, f prime, f double prime, some logarithms, calculator used for derivatives, and limits algebraically. So let's begin with some work on product and quotient rules. For our quotient rule, we want to remember that if I'm taking the derivative of a quotient, I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So in this case, where I have sine x minus 2x squared quantity all over e to the x plus 4 cosine x quantity, I'm going to start with something like this. Okay, the bottom is e to the x plus 4 cosine x times the derivative of the top. Derivative of sine x is cosine x. Derivative of negative 2x squared is minus 4x. I'm going to subtract from that. Zoom in a little bit so I can give myself some more space. The top, so sine x minus 2x squared times the derivative of the bottom. Derivative of e to the x is e to the x. Derivative of 4 cosine x is negative 4 sine x. This is all going to be over the quantity of e to the x plus 4 cosine x squared. At that point, you can stop. Usually, when we do product and quotient rules, you can stop after you get to some kind of a completion as far as the derivative is concerned, and the reason for that is it's often easier to plug in numbers into the problems as is than trying to simplify them and then plug in values for x later. Okay, our second one, we have a product rule. We have 5e to the x times the tangent of x. Please remember, if I'm doing the derivative of the product of two functions, it's going to be the second function times the derivative of the first plus the first times the derivative of the second. Okay, so to take this derivative, I've got my tangent of x times the derivative of 5e to the x, which happens to be 5e to the x, plus my first function, 5e to the x, times the derivative of tangent of x, which happens to be secant squared of x. Once I've taken both derivatives and written them as a sum, I'm done. My third one of these is another quotient rule. I'm really glad I gave this problem and the complexity that it is, because I totally feel like writing this out right now. But that's okay. If I gave it to you guys, I can do it myself. So we get the bottom, 2x squared minus 6x plus 2, times the derivative of the top. Derivative of sine is cosine, so 2 cosine x plus 4 secant squared x plus 6 sine x plus 2 secant x tangent x for the derivative of secant. And that's going to be minus the top, which is 2 sine x, plus 4 tan x, minus 6 cosine x, plus 2 secant x, times the derivative at the bottom, which is going to be 4x minus 6. That is all going to be over 2x squared minus 6x plus 2 squared. I don't feel like I should apologize for the difficulty of that problem, but I certainly feel like I should apologize for the amount of writing you had to do some derivatives there. Okay. Moving on, we have identifying ff prime and f double prime. And we start with this beautiful graph and trying to figure out which graph, A or B, is going to be our function, which one's going to be our derivative. First thing I'm going to try to do is choose one function to try as my derivative. And in this case, I don't know, I'll try A, which is the dashed line. The first thing I do whenever I look for a derivative is I identify any horizontal tangents. And if I look there, at 7.5 I have a horizontal tangent. And again, oh, I don't know, that's somewhere in the vicinity of 4-ish. There's another horizontal tangent. Somewhere down here there's a horizontal tangent. And then somewhere over here. The key is, every time I have a horizontal tangent, the derivative function has to have a 0. So if the function has a horizontal tangent, f prime needs a 0. In this case, that doesn't happen. None of those places on my dotted function where I have horizontal tangents does my solid line function have a 0. I'm going to use blue to talk about the horizontal tangents of my solid function, of function B. First one. It looks like A has a 0 where B has a horizontal tangent. Let's confirm it's at the next guy. Okay, horizontal tangent. Trace it down. I get another 0. So it's looking like, based on these two functions and the fact that I told you this needed to have one function that's the function, the other that's the derivative, we're going to be looking at function B as our function and A as our derivative. So I already talked a little bit about the horizontal tangent when f prime equals 0. The other thing I can look at is whether my function is decreasing or increasing. And I'm just going to zoom in on this interval for B. I'm going to highlight that in blue. And during this interval, B is increasing. Okay, and if I take a look at my function A during that, I'm going to highlight that part in red. That whole time, function A is positive. So when B is increasing, A is positive. Okay, I could do the same thing looking for where B is decreasing. And let's take a look at, I don't know, this section over here is fine. all over here, B is going down. It has an average rate of change that's negative. In fact, there are no points in there that B is increasing. And if I take a look at A in that region, it so happens that A is negative during that entire time. So when B is decreasing, A is negative. That's enough as far as the reasoning for showing why those tangents are true. If you tell me something about the horizontal tangents where f prime has zeros, if you tell me that there's some decreasing or increasing going on, that's enough. You don't need to use all of those words. There's a second one of these graphs that asks you to identify which one is the derivative and which one is the function. And I'm going to start that the same way. I might start with a solid one, which I guess is A. There's a horizontal tangent. Okay, that looks like a 0. There's a horizontal tangent. That looks like a 0. There's a horizontal tangent. That looks like a 0. There's another horizontal tangent. That looks like a 0. Okay. Let's make sure that our graphs are going the right way, because right now it looks like A is the function and B is the derivative. At first, A is increasing, and at first, B is positive. Cool, that makes sense. After that, A is decreasing down to about there, and during that time, B is negative. Okay, that makes sense. That tells me really enough to say that A is our function and B is our derivative. Again, you need to say something about horizontal tangents. You need to say something about increasing and decreasing, and what that means for your pairs of functions. The next section is calculator practice. I just want to remind you in general of the keystrokes. For the most part, you're going to be going into the Math menu. You're going to be choosing NDeriv, and then finding the derivative of each of these lovely functions at those values. As far as the second part, at what value will the derivatives of cosine x and negative 2x squared plus x over 2 be equal? The first thing you need to do is to take the derivatives of each of these. So f prime of x equals negative sine x. G prime of x equals negative 4x plus 1/2. And in these, you're going to find the intersections using the graphing and then calc for intersection. That's as much review as I have for the original part of this, which is just these 3 sections. There are a couple more sections and some chain rule problems that we'll go over today in class.